All right, welcome to the Gen AI interview series, and let's get straight into it. How do you handle the large memory requirements of KV cache in LLM inference? That's the question. And here's the thing, most candidates freeze, or they give one technique and stop. But the real answer is a coordinated attack across 4 layers of the infrastructure stack. That's what we're covering today. One inference engine, one memory bottleneck, 4 ways to break through it. So here's the full picture. We attack KV cache memory at 4 distinct levels simultaneously. OS level, paged attention, virtual memory mapping. Architecture level, GQA and MQA, head reduction. Algorithm level, quantization, data compression. Hardware level, cache offloading, tiered storage. And this is really important. There's no single silver bullet here, no one magic trick. The real solution is all 4 layers working together. That's what production looks like. So let's go through each one. Before we solve it, let's really understand it, right? Because the depth of the problem is what makes the solutions make sense. When an LLM generates text, it internally stores key and value vectors, K and V, for every single token it processes. That's so it can attend back to everything it's already seen. And here's the kicker. As prompts get longer, as batch sizes grow, that cache just keeps climbing. Straight, unforgiving line. Up and up until bam, it slams into the GPU VRAM limit and the whole system crashes. Not degrades, crashes. That's the scalability cliff. Every additional token is additional memory. There's no ceiling built in. And the longer the context, the more valuable your use case, the faster you hit it. So we've got 4 distinct vectors to go after, right? 4 different angles on the same problem. OS and memory management, paged attention. Model architecture, GQA and MQA. Data and algorithmic, quantization. Hardware and routing, cache offloading. Each one targets a different layer. Each one is independently deployable. And stacked together, they're what make high-throughput LLM serving actually work at scale. Let's go through them one by one. First layer, the OS level fix. And honestly, this one's brilliant because it borrows an idea operating systems have used for 40 years. Virtual memory. Here's the old problem. Standard attention demands one single contiguous block of free VRAM to store a sequence. So even if your GPU has 40% free memory, if that 40% is fragmented into small scattered gaps, your request fails. You have the memory, but you can't use it. That's internal fragmentation, and it's a massive waste. Paged attention fixes this. It breaks the KV cache into fixed size pages and slots them into any available space, non-contiguously. Then keeps a virtual mapping table to track where everything lives. Same data, same computation, zero fragmentation. Longer context windows, higher concurrency. This is what vLLM is built on, and it's why vLLM became the default engine for production LLM serving. All right, second layer, the architecture fix. And this one's about reducing how much cache gets created in the first place. Standard multi-head attention stores 1 KV cache per attention head. 32 heads, 32 caches. Full quality, maximum memory. That's your baseline. Multi-query attention, MQA, goes to the extreme. All query heads share a single KV cache. Massive reduction, but you see a noticeable drop in attention quality. It's too aggressive. And that's exactly why grouped query attention, GQA, is the production answer. Groups of query heads share each KV cache, N to M ratio. You still get serious memory reduction and quality is preserved. That's the sweet spot. This is why Llama 2 and Llama 3 both use GQA. Not because it was the simplest option, because it's the right engineering trade-off at scale. And this table is really the punchline for that whole architectural discussion, right? Standard attention, 1 to 1 kV to query ratio. Highest footprint, baseline quality. MQA, 1 to N ratio. Lowest footprint, noticeable quality drop. GQA, M to N ratio. Balanced footprint, quality preserved. GQA is the optimal middle ground solution. Drastically reduces KV cache size while preserving most of the model's attention quality. That's the production winner. And that's the precise answer you give in an interview. Not just shared KV caches, but GQA specifically and why. Third layer, the algorithmic squeeze. GQA reduced how many caches we create. Now we physically compress the data inside each one. By default, KV vectors are stored in FP32, full 32-bit floating point precision. Quantization converts those vectors to INT8 or FP16. Lower precision, smaller footprint. And how much smaller? 50 to 75% reduction in KV cache memory. Yeah, same tokens cached, fraction of the VRAM. And here's what's important to understand. This targets the stored K and V vectors, not the model weights. You're not hurting output quality. You're compressing the cache that sits alongside inference. The accuracy impact during active inference is minimal. Massive storage compression, minimal quality cost. That's the trade-off, and it's a good one. Fourth layer, the hardware assist. And at real production scale, you will need this. Cache offloading creates a tiered memory system, 3 levels. GPU VRAM at the top, fastest, most expensive, smallest. CPU RAM in the middle, NVMe storage at the bottom, slowest, cheapest, biggest. Active tokens, recent context, what the model needs right now, that stays in VRAM. Fast path, no compromise. Older tokens, less frequently accessed context, push to CPU RAM. Inactive historical tokens, all the way down to NVMe storage. Now, and this is critical, fetching data back up from CPU to GPU incurs a real latency cost. This is a trade-off, not a free lunch. So you design your system so the hot path always lives in VRAM and everything cold tears down gracefully. Cache offloading is your overflow valve. The system stays alive instead of crashing. Okay, so let's put this whole thing together because this is where it all clicks. An incoming prompt hits your system. Here's what happens across all 4 layers. GQA first. Structurally reduce the number of KV heads being created. Less data from the start. Quantization second. Compress those KV blocks from FP32 to INT8. Half the size, same information. Paged attention third. Route those shrunken blocks into non-contiguous VRAM pages. No fragmentation, maximum utilization. Cache offloading fourth. As VRAM fills, push the oldest pages down to CPU RAM. Protect the limit. Keep the system running. Result: high throughput serving, long context windows, LLM inference that doesn't fall over under real production load. That is the complete answer. Not one technique, the whole stack. And honestly, once you see this clearly, a lot of other LLM serving decisions start making sense. Why vLLM dominates. why Llama 3 made the architectural choices it did, why quantization is part of every serious deployment. It all connects. This is the Gen AI interview series. Production architecture, the way it's actually built and actually asked. If this session was useful, subscribe so you don't miss the next one. And drop a comment. What's the toughest AI infrastructure question you faced in an interview? I want to know. See you in the next session.